Hi, everyone. This is Charles, and I'd like to welcome you to DCT 302, class number 3. As you know, the webcast webinar business is somewhat new to us, so we're still getting used to it. I'm still getting used to it at my place. I think I should have improved the audio a little bit from last time uh, by hanging a few blankets around my office, basically. And I learned also from reviewing a little bit of the previous sessions that I can speak quickly, more quickly than the last two. So I'll try that and not speak so loud. So at least that seems like it should work as far as I'm concerned. So please pass any comments on either by interrupting by voice or by dropping a message on the chat script in your GoToTraining machinery. That's the preliminary, and question protocol. Well, this is an interactive session, so you're welcome to interrupt. I don't think we've quite got the hands up thing going, although in principle that should work. And nobody's got their hand up at the moment, so we could try that if you want to try. If you have a question, raising your hand, but might be better to just ask a question by the chat script, or feel absolutely free to interrupt at any time. It's the scheme that I'm used to in live presentations, and I'll try to focus my attention accordingly and allocate time according to how relevant I think the question is to everyone else. So we'll give it a try. But the more feedback, the better. I'm happier with more feedback than less, so please feel free. Okay, with that as the intro, let's go. I want to try to do two things today. I'd like to talk about logarithms and finish up with a very serious log coding, slog, relog, silog, sort of log coding thing, completely relevant to cameras at the front end of color pipelines. And then I'd like to spend a little while, maybe 10 minutes, maybe 15 for today, on color gamut at the back end. So that's what I'd like to try to do. And I have visited the forums, and there's some nice little discussions going on in the forums. And I answered a couple of questions with a note saying I'd be happy to talk about that in class. I mean, I did answer a few in text form in the forums, and thanks you guys for interacting on that. And I'd welcome your comments online today if any of you have got follow-ups from the forum questions. So with that, let's go to logarithms. And this is no joke. This is actually my slide rule. I grew up in the era when that was a way to do calculations when I went to university. And the principle of logarithms is a really big deal. So let me walk you through it. Even in the everyday words we use for intervals of time, those intervals are related by being multiples of each other. So let me see if I can draw this for you. So the relationship between a minute and a second, there's 60 seconds in a minute. There's 60 minutes in an hour. There's 24 hours in a day. There's 12 days in a month, and so on up the scale. So you can see the total number of seconds here getting bigger and bigger and bigger by very roughly one digit each interval or each word in common language. Now, here's the multiples, and they're not that convenient. So for science purposes, we'd like to choose more convenient multiples. So one convenient multiple would be multiples of 10. And we talk in common language about 5 figures, 6 figures, 7 figures. We're basically referring to the number of digits after the leading, well, the total number of digits, not including the leading zeros. And the multiples there are multiples of 10, and that's a common one. In fact, that's called common logarithm. Now, for engineering purposes, we use the SI unit multipliers, and they go up by factors of 1,000. So this is kind of a logarithmic measure. The base of the logarithm is 1,000. But that's way too big for kind of photographic and imaging purposes. It is a factor of 10 is commonly used to express sound pressure. So here's the power of 10 sequence of sound pressure measured in decibels, SPL standing for sound pressure level. So here the base of the logarithm is 10, and there's a huge range. Now this slide begins to head toward perception. This is obviously oral or acoustic perception, and we'll use a similar scheme for pictures. And the logarithmic scheme works in both cases because the sense of hearing and the sense of vision responds roughly logarithmically to the physical power levels, the acoustic power level or the optical power level. Now, for vision purposes in the lab, we use powers of 10. We call them density units. But those are too big for ease of use capturing images from the scene. Of course, we end up using base 2 logarithms to measure light level in photographic terms. But let's try to make the transition from this science engineering lab scheme, the power of 10 sequence, into the other sequence. And I'll use as the example my Tektronix 465B oscilloscope, which I still own, although I admit I haven't used it in about 15 years. But if you look really carefully at this oscilloscope, you can see both on the volts per division switch, which is the outer ring here on the knob, it goes in the sequence 1, 2, 5, 10, 20, 50. And it's a similar sequence over here on the microseconds or milliseconds of the time interval. That's, you know, those of you who are familiar with oscilloscopes probably know that it's amplitude in volts versus time. And here again, you see this sequence 1, 2, 5, 10, 20, 50. So what's going on in the case of the oscilloscope is the sequence from one interval to the next goes up in factors of 2, 2.5, 2, 2, 2.5, 2, 2, 2.5. So this is a magnitude, this factor of 2, that's highly useful practically, but squeezing those steps in to merge it to a power of 10 sequence isn't that convenient because there's this 2.5 factor that's not equal to the factor of 2. It's kind of slightly inconvenient. So let's jump then from there to the power of 2 sequence that a photographer would use. And here I show you the numerical values. I'm showing you 8 stops here. And the powers of 2 are highly, highly convenient for photographic purposes. Now, I would also like to tell you, since I'm kind of merging the science and the art here, the science, engineering, oscilloscope, density units on the one hand, and photographic, cinematographic process on the other hand, let's merge those together. And for that, we'll use a little math. Okay, so we've got this numerological coincidence that 10 to the power 0.3 is very, very, very nearly equal to 2. And for science purposes, having these numbers exact makes a lot of sense. And so often, and particularly in the example of quasi-log coding that I'll show you at the end of today's class, it's convenient to use this exact number to define, let's call it a science stop. And instead of having a ratio of 2, it's got a ratio of 1.995. On the flip side, 2 to the power 3 1/3, well, very nearly 3 1/3, is 10. So this says that there's 3 1/3 stops to one density unit. And this is highly convenient. You should remember that number. So that's the numerological coincidence. And expressing that in math, you've got this 2 to the 1/3. Now, earlier we were doing factor of 2 raised to the 3.33 is about 10. So now I'm going to drop down and do 2 to the 1/3 is about 1.259. That's a tenth of a density unit. So now mapping this into what range we're covering, you write the math like this, and obviously this is something you can immediately do in your calculator. You cover a 2 to 1 range in 3 steps by using a ratio of 1.259. Or equivalently, you cover a 10 to 1 range in 10 steps by using a ratio 10 to the power 1/10. That is 10 to the 0.1. And that is very, very, very nearly equal to the same amount. This ends up being 1.260, I think. Now, it's 3 of those increments gets you a power of 2. So 0.1 density is about 1.25 ratio. A 0.3 density is a ratio of 2. So 10 to the 0.3 is about 2. So we talk about a 0.3 ND filter, that's equivalent to a stop. And another way of writing that math is like this. So now what I hope you're seeing here, and I'll show you the next slide, and I think you'll get it immediately, is that this ratio is kind of magic, and it links the cinematographer's preference for factors of 2 to the scientist, the engineer, the laboratory technician's preference for a power of 10. Now, I'm going to skip that one. Now, for those of you who think that a photographer's stop or cinematographer's stop really should be 1024, I can just point out to you that that's not how cameras are labeled. And I guess it's open to question whether you think the design value on the exposure time dial of a camera is 1024 or whether the design value is 1000. I mean, obviously, in a conventional focal plane shutter, the tolerances aren't tight enough that you would be able to tell the difference. And in a conventional photographic light meter, the tolerances are also not close enough that you'd be able to tell the difference. But I think this is just a useful idea for you. So now let's go from that idea. Oh, sorry, I forgot I had a couple more slides. There's some other arenas where this idea of marching up a physical scale by ratios is important. I'm an old electronics guy from years and years and years ago. I used to build the analog electronic circuits, and you know, for any of you that happen to be familiar with that, the resistors have color code, basically because it was difficult to print digits onto the resistor, and then if you soldered it the wrong way around on the board so that you couldn't see it, that would be a problem. So resistors were notated with colored bands of paint, and the colors of the paint read out the codes of the numbers. And there was a standard sequence of resistor values in every decade. So here you might think of these resistors being 10 ohms up to 82 ohms. But then there's another set of resistors from 100 ohms up to 820, and then another from 1,000 ohms, or what we prefer to call 1.0K, up to 8.2K. So this sequence repeated every decade. Now here the steps are not 2 to the power 1 over 3 or 10 to the power 0.1. Instead, there's 12 steps per factor of 10 instead of 10 steps per factor of 10. However, it's exactly the same idea. And let's march to another domain where ratios are used to express physical values. Oh, sorry, I'm missing that slide. I'll show you that slide later on. So now let's dive right into photographic use of this idea. And now I'm showing you 1,000 to 1 range of values, and these are linear light values. So for the time being, you can think of the grayscale scale covering 10 stops. And I'm using science stops instead of true photographic stops. So if I were using true photographic stops, then the numbers on the left would be exact powers of 2. Here you've got on the left-hand side, so picture this as light coming in, and we've got the scale of photographer stops. Now, if they were true photographer stops, up at the top end would be 1,024. But I'm using my science stops, which have got 1,000 at the top end. So instead of precisely doubling every step, you'll see we are doubling in those values, but now instead of going to 64, we go to 63. And then we go to 125 instead of 128, and 250 instead of 256. So these values are absolutely the ones that are used in cameras. So I would argue cameras are actually labeled in science stops as opposed to photographer's stops. But in any event, the key point is we're going up by these ratios of 1.259 every time. And here in the center column, I show you those values rounded to 3 digits. And you can see that there's 3 of those steps to make a stop and 10 of those steps to make a density unit or a decade. So we've got 3 decades worth of range, and this is what we'll talk about in terms of the lab, because this is what the scientists, the engineers, the lab technicians are familiar with. Now, I could also mention the scientists also use decibels, where there's defined to be 20 dB in a decade, or a factor of 10. So another way to look at this scale, this is called 0 dB, this is 20 dB, this is 40 dB, and this is 60 dB. And when red tells you that, well, they think that their red 1 has got a 66 dB dynamic range, these are the numbers that they're talking about. So 6 dB corresponds to a stop, and 20 dB corresponds to a decade. So that's sort of lab science stuff for you. Now, in terms of applying that to digital cameras, think of placing a Kodak grayscale on that logarithmic scale. And in fact, the Kodak grayscale is absolutely arranged in logarithmic terms. And this, I think, is called a Q. If anybody knows, pipe up, either by audio or by chat. But I think this is a Q13 grayscale. Now, there's not 20 patches. There's only 19. because the best that they can do in a printed reflective sample is a density. You'll see that that last chip is labeled 19. Uh, the first one is labeled A, and honestly, I don't even know what that stands for, but that's supposed to be your reference white value. Now, in fact, it's only reflecting 90% or so. But these chips go down in those ratios of a third of the stop or a tenth of a density unit every time. And the chip that's labeled 19 is actually 1.9 density units. Now, I'm drawing this card quite deliberately down at the bottom of the scale because if you're exposing a camera, if you've got light coming in, you will probably expose so that you've got some room in the camera signal above white. I mean, obviously you could expose to take that perfect diffuse white and put it right up at the top of the scale. And you may do that in order to get better performance down in the deep, 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 deep shadows. But typically you'll have a couple of stops above white before the camera clips. So this is a fairly realistic representation of how you might expose a camera. Now, another example for you is this is just the camera looking at the set of paint swatches from my local hardware store. They are also arranged in an approximately perceptual sequence. And that's because our vision sees reflectances and intensities on roughly a logarithmic scale. And this pure logarithmic coding that I'm showing you in this example reflects that visual reality. So basically, that's why we use log codes. So what I'm showing you in my examples in this sequence is basically a coding here where you might want to come in and say, this is code 940, this is code 64, and arrange all the codes on that scale such that they're distributed logarithmically along that range. Now let me show you an example of exactly that. Okay, I think it's this sequence. So you'd better know all those numbers. And based on comments from several of you in the forums, you're familiar with numbers that look like this. So this is just a one-page capsule of the arithmetic that I just told you about a moment ago. Now, picture that scale I just showed you from 1 to 1,000. But now, for reasons that will become clear in a moment, I want you to put the top end at 4,000 because that's the typical integer number that comes off the A to D converter of a contemporary digital cinema camera. And these are not the absolute best cameras. This would be a Red 1 or a Sony F23. I think an F23 has got a 12-bit converter. A silicon imaging camera's got a 12-bit converter. An Epic, an F35, an Alexa, they've all got 14-bit converters. So they're a little better than this. But I want to give you this framework using 4,000 at the top of the scale. And here now on this diagram, I'm plotting the scale linearly. And what I want to suggest to you in this diagram is that there's certain kinds of camera noise where the noise is fixed in its sort of band all the way up and down the scale. So the noise has got this dimension everywhere on that linear scale. And you can see, I think, that as the exposure decreases, the noise band it stays the same width in the linear scale, but it starts to overlap. And so down at the lower end of the scale, the values reported from the camera get confused. And the camera can't tell because of its noise, exactly what the light level was. Now, if you take that diagram and squish it and stretch it into a log scale, just like we had from 1 to 1,000 a moment ago. But now I'm going to show you a realistic mapping of a pure log scale into 10-bit HDSDI from a camera, which then might be recorded on a codex or recorded on an SSD. And I'm just going to use the example here. Now, this is a hypothetical example. I made this up, but I made it up choosing 73 code values per stop of exposure. So I'm allocating exactly the same number of code values to each stop. And that would be characteristic of pure log coding. And I picked 73 because that happens to be the number that goes exactly from 64 to 940 with 12 stops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 stops of scene information. Now, the thing I want you to realize from this is if you look at the previous slide, those noise bands were starting to overlap at the bottom end. So in a real camera, you would see these noise overlaps, and you're not really sure what the signal was. The picture will just look noisy in those dark tones. So if you then stretch out these intervals so that there's 73 codes from a light value of 1 to a light value of 2, 73 codes from a light value of 2 to a light value of 4, there's very little signal going on here. Now, mapping that into the linear light scale, into the perceptually coded scale, and here I'm, working towards this being kind of an S log, RE log, SI log, red log, and so on. Well, there's basically no information there, none. And there's maybe a little tiny bit of information there. And up here, we're starting to get something meaningful. So it's generally not a good idea to use pure log coding because there's too much noise in the blacks. In other words, it's better instead of having log coding where log of exposure translates to video signal by a straight line, it's better to choose a coding where there's some sort of widening of the range at the bottom end. And that avoids this problem of huge numbers of codes being wasted because they're all noise. So this characteristic diagram, going from log of exposure to code value, and typically your camera guys will probably express that. They may want some range reference to 64. Some other people use the idea that you should reference the bottom range at 0. Doesn't really matter. So you might have a reference range 64 to 940, or you might have a reference range 0 to 1023. Doesn't really matter. The principle is you stretch these code levels out to avoid having large numbers of data values in the bottom end being full of noise. Now that feature is then, I call it quasi-log. So quasi being, I think it's Greek prefix, although it could be, Latin prefix. Could be Greek, but I think it's Latin. Quasi meaning partial. So partial log, as opposed to pure log, which are the examples that I've shown you so far. So that's pure log coding. Doesn't work that well. We'd rather do quasi-log. Let's go and see what quasi-log codes we use. Now, we talked about this diagram, if I'm not mistaken, the other day. So I'm going to park that and then go to my big, serious, deep quasi-log diagram. And I know I promised last week that I'd give you some materials. I will do so. I haven't done it yet. So nag me if I don't actually remember to do that, but I'll try to remember to do that by next week. So now let's go over this diagram. So actually, I'm going to use as my starting point a set of formulas. And as I say, I'll give you the handout that gives you this information so you don't have to scroll that down. So basically, the examples that I've shown you so far have been pure log coding. Now, here on the left-hand side of these equations, I'm giving you sort of my kind of mathematical form, log to base 316 or log to base 100. Let's start with this one. This is probably the simplest one. So log to base 100 means that 100 is the base of the logarithmic coding scheme. So what I'm saying is 100 raised to the value x is what yields the linear light value. And the value x, it's convenient if that would go from, well, x here, maybe, sorry, I've only explained this in public a couple of times, so I'm working out the best way to explain it. Well, let's do the explanation this way. This is an equation which could be used at the front end of a camera to do pure log coding. X is the exposure. It runs from 0 to 1. And then you take the log to base 100. Well, first you multiply it by 100, and then you take the log to base 100. So obviously multiplying it by 100 just takes that number to be between 0 and 100. And log to base 100 turns that into 1. Log to base 100 would turn 10 into 0.5. It would turn 1 into 0.01. And the numbers get smaller and smaller. So another way to look at it is use the common base 10 log, and it's just that common base 10 log, half of that. So that's just log math. And you know, there was a question from one of you in the forums, sorry, I don't remember who it was, who completely nailed this logarithmetic. So I thought I would take the license to just go a little further into that arithmetic. Now, the trouble with doing pure log coding, apart from all that noise at the bottom end that I talked about a few minutes ago, is basically taking log of 0 gives you minus infinity. And that's no fun. I mean, either it gives you minus infinity or it just blows up. So your calculator might say error, your Excel spreadsheet would say error. You know, your calculator and your Excel spreadsheet don't know how to do arithmetic with infinities. But this is a big problem. The log function explodes around 0. So to make it practical, what we have to do is clip. And clipping is no fun. Yikes, as I say in the handout. And those of you who know image data know clipping, it's just a no-no. You really don't want to ever have a situation where you clip because people are likely to see it. Now, where we're headed with this discussion is that the need to clip is completely circumvented by a small trick. The trick is quasi-log. And the trick is, instead of multiplying x by 100 and then taking the log, multiply it by 99. So now that number goes from 1 to 99 for all the real exposures, then add 1. I'm sorry, the numbers here go from 0 to 99. We add 1 so that the range is now 1 to 100, and that's a meaningful range over which we can take the log. So now you just take the log. Now, this idea, I've shown you the example of showing you log to base 100, and that's just my way into it. Really, though, this scheme was invented by my pals Peter Sinton and Jan van Rooij at Grass Valley in the south of the Netherlands. I mean, I realize Grass Valley headquarters is in Grass Valley, California, or Nevada City, but these guys are Breda. They're ex-Philips from a long time ago. Now, when they first published their film stream coding, they used this equation. But I kind of reverse engineered it into this equation, and these numbers really just tell you how to code it into a 10-bit HDSDI stream. The kind of abstract math is this math. Now, it turns out David Newman from Cineform invented independently exactly the same scheme, but using 90 instead of 60. So this is SI log coding. Now, the key points are twofold. A, avoid blowing up around 0, and you do that by introducing that little offset. And second, don't have a pure log code that goes from log exposure to video signal as a straight line. Instead, kind of round it or warp it a little at the bottom end. That has serious noise advantages. And this 1+ business, invented by the FilmStream guys, independently invented by David Newman and adopted by Silicon Imaging, and then it turns out adopted by Panavision, RE, Red, and Sony. You know, those are all the other log coding schemes. They all use this numerical trick. So this is what I'm calling quasi-log coding. It's basically what all the cameras do. So now let me give you the single wrap-up slide, and it's a complicated one. It's this one. So this is my codes per stop slide. And let me take a few minutes to go over this, and then we'll stop for some questions. So let me first magnify that, like so. Okay, so what this slide is showing is here's an exposure value going down stop by stop by stop by stop. Now I'm using my science stops instead of the cinematographer photographer stops. So when I'm 10 stops down, I'm down to 0.001. And if you go down in exact powers of 2, you don't get that. So this says I'm 10 stops down. And I'm also showing you density units. They go 0.3, 0.6, 0.9, and so on. So I'm 3 density units down. Now, if I were in linear light space, in 10 bits, I should say here, I would put the top of my scale at 1023. I would have 511 codes in the top stop, because the code value is just going down linearly. There's half as many codes the next stop down. So I get 512 stops in the top stop, 256 in the next stop, 128 in the next. By the time I'm just 10 stops down, well, 10 stops, like, it's a lot. But by the time I'm 10 stops down, if I've got linear 10-bit coding, there's only one code for that whole stop. That's obviously inadequate performance. Now, I've been telling you about pure log 100 coding. And for the sake of argument, in this example, I'm using 8-bit pure log. So I put 255 at the top of the scale. In pure log coding, there's 30, log 100 coding, there's 38 codes in every stop all the way down. Now, that's not bad. However, in the last class, we talked about the 1% rule. We talked about it being the Weber-Fechner number. We talked about 1% being basically the smallest ratio of luminance that any human could ever reasonably see. That math translates into about 69 codes per stop. Now, if you had pure Weber-Fechner theoretical coding, you'd have 69 codes all the way down. And my argument about camera noise is down at 11, 12, 13, 14 stops down, you start getting only a few meaningful codes. The rest is noise. You absolutely do not have anything like 69 useful codes. So you might as well not have this theoretical Weber-Fechner thing, but you might as well start slacking off the number of codes per stop, but not slacking off like linear light coding and not slacking off like some of the other coding we see. So basically, that's the argument that gets us to something like quasi-log 90 coding, and this is silicon imaging. And I'm almost on to quasi-log 60 code. So let me shift over and show you the quasi-log 60 codes, because that's Viper Film Stream. So now let's go to this column, quasi-log 90. This is silicon imaging. And quasi-log 60, this is Viper Film Stream. And this is what ARRI used to call log F on the D20, D21, although now they've discontinued log F. They have a different ARRI log coding, which is comparable, but with somewhat different numbers. And for both of these schemes, I'm giving you 10-bit top end. And now I'm showing you how many codes per stop there are in each of these coding systems. And they're both very, very, very comparable. So there's really not a lot of difference at all. I mean, technically they're different, but in terms of their performance, they're very, very similar. So you can see then that the number of digital codes per stop starts to drop as we get, well, we get 10, 11, 12, 13, 14 stops down from sensor saturation. Now, again, your cinematographer will probably be putting a diffuse white in the scene 2, maybe 3 stops down. So you'll think to yourself, well, okay, a color checker has got about 5 or 6 stops of range in the grayscale chips in the color checker, white being the top one. But you might have a scene where there's elements in direct sun. There's room for speculators up top, but in the shadow, a color checker in the shadow might be down here. So in terms of acquisition, you really want an acquisition where you put the color checker in sunlight somewhere mid-scale. You can have a color checker in shadow and still have some stops left over to deal with really, really, really dark things and still have some speculators. So you'd like to have maybe 12, 13 stops of image information up to the point where you clip the camera. So this quasi-log coding, and here my examples are silicon imaging and film stream. Now, honestly, I did this chart about 2 years ago. I haven't yet included Panalog, Sony log, ARRI log, Red log. You know, these are additional columns in this chart, and you know, it's all looking complicated enough even before we go there. But I should really go and compute that. So now, having shown you that piece of business, that's that basic spreadsheet. Um, and that's where I think we'll wrap today. Now, honestly, I had hoped to get to wide gamut color, but we're going to do that next time. I'm just letting it flow as it goes here. Um, and I hope you found that to be a useful uh, description running from the theoretical math foundations all the way to the details of the math. And as I say, at some point I'll have to fill in exactly what those numbers are for RA log, red log, Sony log, and so on. Um, but that's the story of quasi-log coding. So with that, let me wrap up my presentation and then open up to questions. So feel free to just pipe in by voice. That's probably what I prefer. But if you'd like, you can also key a question into the chat channel, and we'll take it from there. So Peter's asking a question. How do the stops on a camera, 1, 2, 4, 8, 16, and so on? Oh, Peter, so you realized that the camera f-stops go in a different sequence. They go 1, 1.4, 2. So it's a stop on the f-stop ring is 1.4, then the next stop is 2. Now, ordinarily on the f-stop ring, you'll feel click, click, stop, click, click, stop, click, click, stop. So you are actually controlling the aperture ring in third of the stop increments. But Peter, you're asking, where do those numbers come from? And it's a simple explanation, but it's a subtle one. So let me just see if I can draw this for you by just freehanding a sketch. So basically, let's say it's rare to find a camera that goes down to f1. It is possible, and most of you have seen cameras that go down to 1.4, maybe even 1.2. But for our purposes, let's take an f-stop of 2, and virtually all cameras have got an f-stop of 2, and that would have an aperture that I'd like to suggest has got this diameter. Basically, when you go to an f-stop of 4, you have the diameter. So the reference to the diameter of the aperture, and the aperture is actually a variable circular aperture in the middle of the lens, and it's made by these sort of little leaf elements of sheets of steel that close up using a cam as you rotate that ring. So basically, at f, you write this as f over 2. The 2 serves as a denominator. And we write this as f over 4. The slash indicates that the 4 serves as the diameter. That's measuring the diameter. The key point is that the area is not half. The area is a quarter. So when you go to f over 1.4, well, 1.4 is the square root of 2. So the area of f 1.4, the diameter is f over 1.4, but the area is half. So what this means is from f over 2 to f over 4, that's a half. Halves the amount of light, that's 1 stop. When you go from f1 over 4, I'm sorry, where did I get screwed up here? You know what, I screwed myself up somewhere. I guess here's my screw up, and sorry about that. I'm winging this and doing it on the fly. Going to f over 4 makes the area 1/4. And we want an area that's 1/2. That's F over 1.4. So, oh, Dirk, you're right. It's my mistake again. As we stop down, no, this is right. F over 4 this is correct because the aperture has a dimension that's the focal length divided by 4. I'm sorry, this number is wrong. This should be 2.8. That's my mistake. Okay, and F over 1.4, that would be a bigger circle than F over 2. Okay, my mistake. You know what? I'm going to take this description and work up a slide on it. And you know what? I'm going to commit to you, I'm going to do this for next class. So rather than starting from scratch, and well, maybe we will just start from scratch and run this through one more time. So I started with F. It's the focal length of the lens divided by 2, which is the diameter of the aperture. And if I were to go to the focal length divided by 4, that would have the diameter, but that would reduce the light to 1/4 of what it was. So in order to reduce the light by half, I go to F over 2.8. And that's then one stop. That's what reduces the amount of light by half. And so you will find a label typically at F2, a label at F1 at 2.8, a label at F4, but you'll find little clicks, you'll find labels at those points, but you'll find a click stop here and a click stop here, and a click here and a click here. If we wanted to double the light, we would go to F1.4, and that diameter wouldn't be double the diameter of F1.2. It would only be 1.4 times the diameter. And again, you'll find click stop here, click stop here. There's the explanation from the top. But as I say, this is something that I've not really explained in public before. It's a great question. It's a really valuable little linkage piece between my camera exposure 1,000 to 1 or 4,000 to 1 or million to 1 range and how the cinematographer controls that exposure. So I really like the question, and that's what the explanation looks like. So let's see, we're not quite at the top of the hour. We've been going an hour, even though I really only kind of planned to go 45 minutes. Time for one more question. Peter's saying scientific stop would be 1.248. Well, in terms of f-stops on an aperture, it would be 1.414 or something or other. In other words, exactly this 1.4 number on my scientific sequence would be precisely root 2. Then this would be 2. This would be 2.828. In other words, scientifically 2 root 2. These things start to diverge when you get to little tiny apertures, because the scientific aperture is f over 23.2 something, but photographers always write that f22. So you know, basically nobody is using the theoretical stops. They're writing them with this standardized sequence that goes 5.6, then 8, well, everyone agrees on 8, and then 11, where scientifically it's actually, I think, 11.6. They round the wrong way, and so on. So in terms of the aperture, it's my scientific stop numbers 1, 2, 4, and so on, but with additional aperture stops halfway. So I think that kind of gets that. But I'll write that up. I think that's a really great question, and it's a good addition to the standard course material here. So you know, FX PhD guys, you're kind of cutting a new path through some of this material. So is there one more question you want me to take before we wrap it? Okay, so my second hand just crossed the 12 here. We're an hour in. Let's wrap it up there. If I remember correctly, but John and the FX PhD crew will send email and post notes to this effect. I think a week today we're back to our typical time schedule, which accommodates East Coast and Europe. Not so convenient for Asia, although I did notice somebody today, Shailendra, if I'm pronouncing that correctly, is with us from Singapore. So I absolutely appreciate that you're joining up from Asia, and I hope we get a chance to do another Asia time zone event. So there you go. Thanks for participating. We'll wrap it there, and we'll see you next week. Thanks all.